Before moving to the gradient computation, let me just reiterate the data flow within a VAE so that the discussion on gradient computation is well appreciated. So in a VAE, we have two neural networks, encoder and decoder. A data sample X goes as an input to the encoder network, and encoder network outputs the parameters of the latent distribution Q phi z given X, that being a probabilistic neural network. Then a sample of Z is obtained by sampling through the distribution whose parameters that the encoder network has predicted. So taking the parameters of the distribution that the encoder network has predicted, we will sample one or many points of Z, okay, which is the actual latent vector, and that latent vector that has been sampled outside of the encoder decoder will go as an input to the decoder network, which would output the parameters of the conditional data distribution p theta of X given Z, right? So three things are happening. One, data goes as an input to the encoder, which will give you the parameters of Q phi of Z given X, and having the parameters of Q phi of Z given X, there's a sampling that is happening outside of the neural network, and once we have the sample from the latent distribution, and that sample is taken as an input and given to the decoder, that sample is taken and given as an input to the decoder network, and decoder network outputs the parameters of p theta of X given Z. This is the procedure of how the data flows into a VAE. Please note that there is a sampling procedure that happens, that is there in the pipeline, that is outside the neural network. So this is a critical point to be noted, because this comes up in the gradient computation. So there is a sampling network, there is the sampling procedure, beg your pardon, it's not a network, it's a sampling operation that happens outside of the encoder and decoder neural networks. Okay, now let us proceed with the gradient computation. Now what we should do is that we should look at the loss function, which is the elbow, and we need to compute the gradient of the loss function with respect to the encoder and the decoder parameters. Okay, let us look at our loss function. So the loss function that we have contains two terms. The first is the conditional expected data likelihood, and the second term is the KL divergence. Okay, so just for a reference, let us have our loss function here. Now what we need to do is that we need to compute the gradient of this particular term with respect to the encoder parameters phi and the decoder parameters theta. So now, since we have represented the encoder function using a neural network, all of these will be parameterized by phi, right? All the q will be parameterized by phi now. Okay, so now let us compute the gradient of each of these terms with respect to both the encoder and decoder parameters. So there are four gradients that we need to compute. The gradient of the first term in elbow with respect to phi, the gradient of the second term in the elbow with respect to phi, and similarly with respect to theta. So there are four gradient terms that we need to compute. Okay, so let us start with computing. To compute the gradient of the loss phi with respect to the encoder parameters phi. Okay, let us first consider the encoder parameters phi. Now, which means that we need to compute the gradient of the first term, which is the expectation of, so let us go term by term. This is the log of p theta X given Z. The expectation is with respect to Q phi of Z given X. Okay, and also note that the Z that we are conditioning it on is also coming from Q phi of Z given X. Right, this is what we have. We need to compute the gradient of this particular term with respect to phi, and we have this term depends on phi on two counts. One, the expectation is with respect to Q phi, and the conditioning variable here, from which we are sampling from which we are having in the loss, the conditioning variable is also sampled from q phi of z given x, and there is dependence on phi there as well. Okay, we need to compute the gradients now. Okay, now the above term looks like the following. The above term is similar to, just to avoid writing the log p theta x given z every time, I can write this as, we need to find the gradient of expectation with respect to a distribution. Let's call that some p psi of v. Okay, and we have a function f psi of v, and the gradient is with respect to psi. Okay, so now here the distribution p psi that we are talking about is q phi of z given x, and the function with respect to which we need the gradient is log of p theta of x given z. So please note that this function also has been shown to be having dependency on psi, because the z, the conditioning variable, is sampled from q phi of z given x, and therefore that also depends on the parameter with respect to which we need the gradients. And we have replaced the random variable v with the random variable z here. That's all. Whatever we had as z is been written as v now, and the parameters psi that we have here are represented as the parameters phi that we have in our original problem, right, is represented using another set of Greek letters psi. Now, why did I do this? This is because I just wanted to avoid writing log of p theta of x given z every time. Okay, so this is the form of the gradient that we need. Okay, now how does that look like? Let us write that down. So this is equal to, so gradient of expectation of some function with respect to a distribution is equal to, let's write that down. So this is the gradient of the expectation. The expectation by definition is the integral, assuming that all of them are continuous random variables, which is the case in our current scenario, f psi of v dv. Okay, right, so we know that the gradient is a linear operator, so we can push the gradient inside the integral. So this is p psi of v psi of v dv. Okay, just push the integral inside. Then once we have the gradient of product of two functions, if we want to find that out, we need to put the product rule. So product rule tells us that this is the gradient of this function times the second function, which is p psi of v, just applying the product rule of gradients or differentiation here, dv plus the second term is, I can split the integral because again integral is linear. So we have the gradient of the second function, which is this, times f psi of v dv, right? Just applying the product rule of differentiation. Now, what is this function? If you carefully look at this particular function here, this can be written as another expectation of the gradients of f psi of v with respect to the distribution as p psi here, right? Because this is some function, the gradient of f psi is a function, and we have the density function here, and the integral of the density function with respect to some function is expectation by definition. But second term here, right, which is not an expectation. So this term is not an expectation. Okay, not an expectation, and therefore It cannot be empirically computed. Right? So we know how to compute expectations by taking sample averages, right? So this can be evaluated because this is the if you look at the current scenario here, our f function is log p theta of x given z, and we can compute the gradient with respect to that. Okay, and because we can obtain samples from this distribution q phi of z given x. Okay, so this expectation can be computed using sample averages. However, the second term here that comes up cannot be computed because it is not an expectation. Why is it not an expectation? Because f psi of e is not a probability density function. Had it been a probability density function, we can write this integral as an expectation. But because it is not a probability density function, this integral is not an expectation. And because it is not an expectation, we cannot compute that using sample averages. Okay, so we have the gradient of the density which has no interpretability, and therefore you cannot write the product of the gradient of a density function times some other function as an expectation. Okay, therefore this gradient, which is what we need, cannot be computed. So this implies that the gradient of the expectation of log of p theta x given z with respect to q phi of z given x cannot be computed. So here by definition, the z here is coming from q phi of z given x, right? Okay, this is the bottom line. So to train the neural networks, which are the encoder network here, we need to find the gradient of the first term in the elbow with respect to phi. Okay, that cannot be computed because the product rule of differentiation, when applied to this particular gradient that we need to compute, we will end up having a term that cannot be computed in terms of expectations or sample averages. So this term cannot be computed, and therefore the gradient that we need to train the encoder neural network in a VAE cannot be computed. So the other way to say it is, look at this. If you look at the data flow diagram here, what we are actually saying is that there is a sampling step that exists here, right? So what happens is x goes through the encoder, so you get some parameters and there is a sampling. So if you look at this entire thing as one pipeline, what's happening is there is a neural network, there is a sampler, and there is another neural network. Okay, and we have p theta of x given z. So if we need to backpropagate our gradients all the way from the output of this decoder network, okay, we can do that. We need to then backpropagate our gradients through this sampling network, or rather sampling procedure, right? And then we have to go propagate those gradients all the way to the input of the encoder network if we want to train the encoder network. Okay, now that cannot be done because the sampling procedure that is there is a non-differentiable operation. Okay, so there are lots of functions that are non-differentiable, right? Sampling is one such function that cannot be differentiated. Okay, so since the sampling here cannot be differentiated, you cannot propagate the gradients from the output of the decoder all the way through the input of the encoder network, as there is a sampling procedure that is in between the encoder and decoder network. Okay, so now how does that translate to math is that when you try to compute the gradients, and look at this, if you look at this carefully, what is happening is that you need to compute the gradient of an expectation of log of some function, and this function is dependent on a random variable z. Okay, and this random variable is obtained through a sampling procedure, and that sampling also is dependent on the parameter phi with respect to which you are taking the gradients. Okay, so now because the z depends on q phi and you are seeking gradients with respect to phi, it turns out that when you do the maths, the gradient of this particular expression, okay, with z coming from q phi of z given x, cannot be computed with respect to phi because of the existence of a sampling operation which is non-differentiable. Okay, so now how do we solve this problem? So if we do not solve this problem, there is no way that we are finding out the gradients of the encoder parameters with respect to elbow. So to solve this, the authors in the original VAE paper proposes this solution called solution for this problem is what is called as the reparameterization trick. Okay. So authors uses a trick called reparameterization to make the gradient computation feasible. Okay. Now, how do we do that is the question. So, reparameterization is a well-known technique in classical statistics where one can represent a random variable in terms of another random variable using a deterministic function. So, let us see how that is done. So, let's recall that the gradient of the expectation of this particular function cannot be computed, right? This is the problem that we are dealing with. How do we solve this problem? Now the idea is express the distribution or the density function, express the distribution p psi of v in terms of another distribution involving another random variable, auxiliary random variable, which is independent of the parameter psi. Yeah. The idea is to represent the distribution which we are sampling with respect to. Okay, so here too, let me just complete this story. This v is coming from p psi of v, right? It's coming from the same distribution as we are computing the expectation with respect to. So what we need to do, the idea in reparameterization is to represent this density function using another auxiliary random variable that is independent of the parameter c. Now, how do we do that? Let's say that we have suppose, so concretely, mathematically, this is how we do this. Suppose there exists, in English, suppose there exists an auxiliary random variable. Okay, let us call it epsilon. So that is sampled from some distribution p epsilon. Now this p epsilon is independent of psi, right? So p epsilon is not dependent on psi. Okay, and we can write v, which is the random variable of interest, in terms of some function g, okay, of epsilon. So then what happens is the following. So what we need is the expectation of this function f psi of v with respect to p epsilon of v, right? So this can be shown to be equal to the expectation of f psi of, so what is v here? V is g of epsilon. Okay, so now this g function depends on the parameter psi here. Okay, so this is f psi of f of g of epsilon. Let's so rather I will omit it because f already has the dependence. Okay, so now v is given by f psi of V is given by G of epsilon, but now this expectation now is with respect to P epsilon, not with respect to P psi. Okay, so please note the difference here. The expectation which was with respect to P psi now became an expectation with respect to P epsilon. So this result is a known result in statistics. This is called the law of unconscious statistician, or abbreviated as LOTUS. Okay, right. So this will tell you that an expectation with respect to one random variable can be written in terms of expectation of some other random variable. So let me just expand this. This is the law of it has a peculiar name. So idea is that the expectation, if there exists a function that transforms one random variable to the other, so here epsilon is getting transformed into the random variable v, then expectation of a function with respect to one random variable can be written in terms of the expectation of the function with respect to another random variable, just that the arguments here for this function has to be changed by g of epsilon. So this is what the idea is. Okay, now of what use this is for us is the following, that now we are seeking the gradient of the expectation of this f psi of v with respect to p psi of v, right? Now this gradient is with respect to psi. So this is equal to the gradient of the expectation of f psi of g epsilon with respect to p epsilon now. So note, what did we do? We removed the dependence of the sampling step, okay, or rather we shifted the sampling step, okay, out of the expectation. So now with this, what happens is, while the gradients are with respect to psi here, the expectation is not with respect to a distribution that depends on psi, correct? Now this here psi is being sampled from, the epsilon is sampled from p epsilon, which has no dependence on the parameters with respect to which we are taking the gradients. Now this can be approximated in terms of sample average. So what we can do is that we just take the usual law of large numbers, and this can be written as j equal to 1 through m. So f psi of g of epsilon j, of epsilon j, where the epsilon j's are sampled from p epsilon, right? So now this gradient that could not be computed now can be computed. So just recall what we did. This gradient could not be computed because the gradients was with respect to an expectation, and that expectation was being computed using a density function which had dependence on the same set of parameters with respect to which we are seeking the gradients, right? So that's what created this particular problem, right? It just we ended up having an integral that cannot be computed. Now what should be done is that if we can somehow write this expectation with respect to another density function that is not dependent on the parameter with respect to which we are taking the gradient, then we are done. Okay, how do we do that? The way to do it is that express the random variable upon which this density function is defined in terms of another random variable, okay, another random variable. So another random variable whose density function does not depend on the parameters with respect to which we are seeking the gradients. Then the law of the unconscious statistician will tell you that this expectation can be written in terms of the expectation with respect to this another density function that is not dependent on p psi. So the passing the gradient with respect to the sampling step. So look at it, right? So we have the gradient here. We need to take the gradient with respect to psi, and this gradient has to pass through this quote unquote pass through this sampling step here, because this is the sampling that we are doing when we are taking expectations. What did we do is that when we write this expectation with respect to another random variable or another density function that does not depend on the parameter with respect to which we are seeking the gradient, then the gradients need not pass through the sampling step. So that is the idea. Okay, so then we can use our usual law of large numbers to compute the gradient that we are seeking. With your pardon, there should be a gradient parameter here. J is 1 through m, and we have the gradient of this particular function with respect to psi, which can be computed now. Okay, so that is the idea. So this entire process is what is called as the reparameterization trick, where one random variable is being represented in terms of another random variable using a deterministic function g, which would enable gradient computation easily. So that is the idea of reparameterization. So let us look at the examples of reparameterization to better understand this point. Examples of reparameterization. Okay, so let us look at the first example that is commonly cited in the VAE literature. Let's say that the latent posterior that we have, okay, we assume that this is a Gaussian distribution, okay, and this Gaussian distribution is on the latent variable, of course. Let's say that the parameters of this Gaussian distribution are mu phi of x, comma sigma phi of x. Okay, so why did I write mu phi of x and sigma phi of x is because of the following. So recall that in a VAE you have the encoder network. The encoder network is giving you the parameters of the distribution q phi. So what happens is the encoder takes as input the input sample x, okay, and this is the q phi network, and now you are getting the parameters of this distribution. So we have assumed that this q phi distribution is a Gaussian distribution, which means that this will give you a mu and a sigma, okay, and this mu and sigma are parameterized by phi, right, because it depends on the parameters of this neural network, and this is also dependent on x, because for every given x, right, so for a given x this distribution is different. Okay, so you have a different latent distribution for every given sample of x, and therefore you have the dependence on x for the parameters of this distribution q phi, right. So now also note that we are only assuming that this distribution q phi of z given x is Gaussian, which means that we are not saying that this is a particular Gaussian. We are simply saying that it is a Gaussian distribution whose mean and variance are being obtained from the output of the encoder network. Okay, so what are these mu and sigma? These are the parameters of q phi of z given x for a given input x, right. Okay, so this is under the assumption that my q phi of z given x is a Gaussian distribution with a certain mean and variance. This neural network is going to give me, the encoder neural network is going to give me the particular mean and the variance of the distribution that I have assumed on the latent posterior. Okay, now how do we reparameterize this is the question. So now let epsilon, which is the auxiliary random variable, be a Gaussian, okay, with zero mean and identity or unity as variance. Then it's a well-known result in statistics that any random variable, a Gaussian random variable, can be reparameterized or written in terms of a normal distribution, right. So this is mu phi of x plus sigma phi of x times epsilon. So depending upon what the dimensions of this thing is, right, I mean this will become a Hadamard product, which is an element wise multiplication. But if you take a normal distribution with, or a Gaussian distribution with zero mean and unit variance, if you just add a particular constant mean and multiply the sample from a normal 0 1, then you know that Z will be now sampled from a normal distribution with mean equal to mu phi of x plus, mu phi of x, and the variance will be equal to sigma phi of x. So this is a known result that any Gaussian distribution with a certain mean and variance can be reparameterized in terms of a normal distribution, which is a Gaussian distribution with zero mean and unit variance. Okay. Now, what is the g function? This is the g function. So this is g of epsilon. Okay. So g of epsilon is this particular operation that given a particular sample from normal 0 1, you take the output of the neural network, which corresponds to the mu and sigma, multiply that epsilon with the sigma, and add that with the mu. Okay. So now, as I said, if we are working with vectors, so then this happens to be the dot products or Hadamard products, or rather we can write that this will be a matrix and this will be a vector of appropriate dimension. So this will be a matrix and vector product. So depending upon what the dimensions of your Z is, these are all vector operations. However, if you reparameterize a sample from the normal distribution using this particular function, then your Z comes from a Gaussian distribution with that Z and given sigma. Okay. So now what is this function? This function G is actually mu plus sigma times epsilon. So this is that function that we are talking about, which we showed here, right? So the Z, or the random variable of interest, was now represented with us using another auxiliary random variable and the G function. In this case, the G function happens to be an affine transformation. This is called an affine transformation, which is taking a mu and sigma and scaling your epsilon with that particular sigma and adding that particular mu. Okay, so that is the idea. This is one of the ways of reparameterizing. There is another way of reparameterization, which is called the inverse CDF method. Where suppose Z is a random variable and Fz of Z denotes its CDF, cumulative distribution function. Okay, then if you define Z cap as the inverse of the CDF, where, okay, let's call this epsilon, where the epsilon is sampled from a uniform distribution between 0 and 1. Just write it as Z itself. Okay, so now this is another reparameterization. The idea is that one can express any random variable in terms of a uniform random variable between 0 and 1. Okay, so now the G function here is simply the inverse of the CDF. Inverse of the CDF, and the epsilon is from uniform 0 1. So uniform distribution between 0 and 1. I'm saying, so one can reparameterize any continuous random variable using the inverse of the CDF of that particular random variable, and you operate the inverse of the CDF on a uniform random variable, which means that you take a sample from a uniform random variable between 0 and 1, you pass it through a function which is the inverse of the CDF of a particular random variable, then the corresponding output that we get will have the same distribution as that of the random variable whose CDF inverse we are looking at. Okay, so this is called the inverse CDF method. So this is also a reparameterization method, because what we have done is we have represented one random variable z using another random variable epsilon using some function which happens to be the inverse CDF. Okay, so these are two examples of how one can use reparameterization in the VAE setting. But typically in an implementation, from an implementation perspective, people assume q phi of z given x to be a Gaussian random variable with a certain mean and variance, and the affine transformation is what is used as the reparameterization. Okay. So please note that the first example that I gave, which is this particular form of the g function, is specific only to q phi of z given x being a Gaussian distribution and the auxiliary random variable being normal 0 I. Here in the second example that I cited, this sort of reparameterization is common for any continuous random variable whose CDF and its inverse exists. Okay, but as I said, the usual practice is to assume that q phi of z given x is a normal distribution and use this kind of reparameterization in a VAE setting. Okay, so note that this choice that we are making on q phi of z given x, that it is a Gaussian random variable, is a design choice. So one can make any other choice on q phi of z given x and parameterize that using the encoder network. The only thing is that one needs to find a g function and an auxiliary random variable using which we can reparameterize that. Okay, yeah, that's the only condition. However, the usual practice is to assume that it is a Gaussian random variable with this particular mean and a variance, and reparameterize using normal 0 1. Okay,